let me take this opportunity to introduce Austin, which I had many things I was going to say, but I'll make it super quick. So Austin is a researcher at Google. He's done phenomenal work on the surface code. And the one thing which I think has been really great is the connection of how you go from this idea of a topological code to implementation and practice. And at Google, of course, he works on it on superconductors, but he's also done some nice work with the University of Sussex, basically looking at how could you also do it with trapped ions. And that's it. Good to see you, Austin.
Thanks. All right, so let me share my screen. Let me know when you can see the slides.
Looks good.
Great. So I'd like to really try to make surface codes as practical as possible today. So the first 2/3 of the lecture, we will focus on the theory in a very abstract manner. But then we also want to come back and see, what can you actually do in hardware and how that impacts the theory of how you actually implement these things. So to get right into it, the surface code is a particular pattern of stabilizers. You have a 2D lattice of qubits, nearest neighbor, square grid, and then you want to measure X stabilizers. So these are the guys that detect Z errors, the dark ones. And you want to measure Z stabilizers, the ones that detect bit flips. So as I hope you can see, if you look at that, that means that if I have, for example, a bit flip here, I'm going to show some kind of detection in these two locations. And I can use that pair of detection events to then say, well, most likely explanation of two detection events here and here is that there must have been an error here. And this checkerboard then allows you to cope with a very diverse range of local errors. You can have really kind of any sort of splatter of mess, provided it's local, the code will say, here's a bunch of detection events, and it will allow you to correct it. So digging a little deeper, we don't have magical stabilizer measurement devices. That's not how life works. We have to implement this with 1 and 2 qubit gates. And that's not at any level a bad thing. By forcing ourselves to use 1 and 2 qubit gates, it limits how noise can propagate and indeed gives us predictable ways in which noise can propagate. Here's an example of a bit flip occurring halfway through that circuit. And then you know that it's going to lead to a pair of phase flips on precisely the last 2 qubits that get touched. So in this particular example, you can see that the last 2 qubits as numbered, qubits 3 and 4, so these are time ordering numbers, are perpendicular to the logical operator. And so we can control this double error to be perpendicular to our logical operator to prevent it from eroding our code distance. If we had organized these numbers differently, organized these 2 qubit gates differently, and we'd had a double ZZ error along this direction, then that would mean that you could create a chain of Z errors using fewer physical errors. So this sort of amplifies a single error to a double error. We make it benign by controlling the circuit order. So these are important details to keep in mind when you implement topological codes. You really need to carefully tune the underlying circuits to get the full code distance. If we wish to talk about the surface code as human beings, it helps to simplify things. Working with a great big 2D lattice of circuits is a bit too much to chew on. So what we're going to instead do is focus on just these 5 qubits. So 3 data qubits and 2 measurement qubits. And we're just going to focus on this slice. So these will be just ZZ measurements, stabilizers. We're looking for bit flips. This is a little piece of repetition code. And that little piece of repetition code will contain all the features that we need to really talk about how the surface code as a whole works, plus being amenable to 2D slides. So here it is. Here's our little slice of surface code. It is a repetition code, but now we can play games like, all right, here is my slice of circuit. Here is my error that just happens to go here, and then we can follow the propagation through. At this point, you might be wondering, what are these plus and minus gates? So this is a little bit of a throwback to the fact that I work with superconducting qubits these days. Normally, you'd expect to see Hadamard gates here and maybe CNOT gates here. We have CZ gates, and these pluses are a plus Y/2 rotation and a minus Y/2 rotation. So it is just easier to do that. Rotating around one axis is easier than doing the true Hadamard gate, which is sort of 45-degree rotated axis. That's actually pretty much a pain to implement and is unnecessary, provided you can bring the zero state to an equal superposition, even with some phase between it, and then bring it back. That's good enough for the purposes of error correction. So here we have an example where a bit flip flips a bunch of measurements, because it stays here, of course. These measurements don't make that error go away. And indeed, it's very important to emphasize that when we do error correction, we don't actually correct these errors in hardware. Those errors stay there. So if an error occurs, you will see a permanent flip of the measurement sequence at the point where it actually gets detected. So here, the important thing to take away is it's the changes in measurement values. The fact that this went from 0 to 1, this is a detection event here. The fact that this went from 0 to 1, this is a detection event here. So what can we do with that? Well, before we even switch our quantum computer on, we can go and put every possible error in every possible location and work out where that error would be detected. So for example, here is an X error. If we trace it through, it would be detected here and here. For graphical representation purposes, we're going to say that a detection occurs lined up with the initialization. Why? Because it just allows me to draw a line between those two initializations and draw the error on that line. And now what we get when we put every possible X error in every possible location is we get a graph. So here we can see this X error leads to a detection event here and here, and so on. You can build up every possible error. This measurement error here will lead to a detection event here and here. And all of this is done completely in classical software. In practice, you don't just limit yourself to X errors. You put X, Y, and Z errors. You put 2 qubit errors, and you work out everything, where everything is going to be detected. You build this nice graph. Any particular graph edge is in general going to have many possible errors that can lead to it. And you'll also know from your error model what the probability of each of those errors is. And that allows you to then also calculate the total probability of each line in the graph. So you get a weighted graph from your error analysis. So what can you do with that? So we have a graph. I've now expanded the example. This is still repetition code, but now we have 10 data qubits, just so I can show a bit more about how the information gets processed. And let's imagine that this little green dot represents a single detection event on that graph. So we've had a chain of zeros, for example. It's become the beginning of a chain of ones. We have a detection event, and we have some information. So how do we then go and process that? Well, the algorithm looks a bit like this. You explore the graph uniformly in all directions. In this instance, we find a boundary. So this is the edge of our code. And what that means we can do is we can choose it. So we're going to play a game of drawing circles around dots. And you'll see how this goes. So now we have some more dots. We draw some more circles. And we find that they've collided. And the mathematical condition is basically, provided we can draw these circles in a non-overlapping manner, you can match them together. And if you do so, you can show, through a bunch of math we're not going to go through, that this gives you a little piece of a globally optimal solution, meaning you can match all of your detection events either to a boundary or to one another, such that you use the minimum total number of edges and indeed the minimum total weight of edges. So this is the minimum weight perfect matching algorithm. So you go ahead and match them. We've satisfied that condition. You go match them. Then we go get some more data, play this game again. Now we've hit the current time boundary. So we know when we're running this algorithm that we do not have enough information to actually do anything with this. So we move on, wait for a bit more information to flow into the computer, expand, hit a boundary, match, keep going. More. Now we've had two colliding ones. So again, we have a condition we can match these. We keep going, play this game. There's one more example I want to talk through. Well, what happens if you have this situation? We have a cluster of detection events. We've done an expansion. We've found a matched pair. And then we play this game again. And now what? Well, the answer is you start pushing and pulling your circles. So we're going to push this one smaller and pull this one bigger. So it looks like this, but we still have a collision and we can't do anything. Now what? So in the algorithm, you create what's called a blossom, which is a fancy way for saying you draw a moat around everything and you just keep expanding. We've hit the current time boundary, can't do anything, wait for more data. All right, now we've hit the wall and then you can rejig it. And yeah, there are a whole bunch of details in terms of making sure this all works smoothly. But what are the key takeaways? So the key thing to take away is that this algorithm runs as the data arrives and it keeps you close to current time. You don't have to wait for some big chunk of data and then process it blind to the existence of the time boundary. The time boundary exists in the algorithm, and this allows you both to process quickly and with very low latency. Ideally, you staying right up at current time. And that will become important later on, because at some point, not only do you need to perform error correction, you need to perform it with low latency so you can tell your computer what you want to do next. For the moment, just hang on to that fact. All right. So we've talked about analyzing the graph in terms of X errors, Z errors, building a graph. Great. So here is the surface code again. Here is what you can imagine comes from analyzing the Z errors, and here is one that comes from analyzing the X errors. Fantastic. But there's more information available, because when you have an error model, it's typically balanced, meaning if there is some chance of having a Y error, which leads to both. And so what can you do with that? And the answer is pretty simple. If you have a Y error in this particular location, so that in particular corresponds to this edge and this edge, well, there's a correlation then between those two types of errors. If you have an X error, there's a 50% chance what you're really seeing is a Y error. So when you believe an X error is present, you can then go and say, you know what, there's actually now a 50% chance there's a Z error here too, and you go and change your graph. So you can introduce correlations into your graph to give you hints about what you should do. So to take this specific example, without taking into account correlations, this would just look like a Z chain physically. You would not be able to see it. You would just get a single detection event here, here. And using minimum weight perfect matching, you would say, well, maybe I should match it over here. That's two edges of equal weight. Or over here, that's another two edges of exactly the same weight. So you would have a 50-50 chance of failure, and you would get a logical error half the time. Instead, because we have these detection events as well, so this is related to detecting X errors, we have these. We're going to say, well, this one's clear. I can match this case, two detection events, match them to one another. And because we have a belief that this is present, we can then go and reweight this edge here to say, well, this one has a 50-50% chance of being present. And when you do that, you break the degeneracy between these two cases, and you're going to preferentially choose this one. And this pattern of errors now becomes guaranteed correctable. The details are more complicated in practice when you're using a fully 3D graph, but this certainly illustrates the principle, and you can show that it works in practice. So these are simulations of the rotated surface code. This is the green lines are when you don't use correlated information, and the orange lines when you do. So main takeaway from here is the general target error rate for a computer using the surface code is 10 to the minus 3, which is a very modest target. Of course, no one in the world can do that yet, but it's still considered a modest target. And when you get to that level, at least in simulations, you're assuming equal time gates and equal error, which is of course not the case. But if you did assume that, you would get a factor of 10 suppression every time you increase the code distance. So every time you go from distance 3 to 5 to 7 to 9, you get a factor of 10. And that allows us to extract this very simple argument that when you use the surface code, you can get the logical error per time slice using this formula. So very robust exponential suppression of error with modest resources. Moving on. So to date, we have talked only about doing identity gates. We have a logical qubit. We talked about going through multiple rounds of time, how you do error correction, how you keep it up to date. But the only thing you can do with that, as drawn, is an identity gate. And we can represent that using this picture. So if you look at this figure, you see a dark edge here, light edge here. dark edge here, light edge here. So this cube represents D time slices of performing D rounds of stabilizer measurement. And we have 3 D time slices here. Of course, we want to do more than that. And so this is how you start the process of doing more. Let's imagine we have a logical qubit, and then we just initialize a sea of zeros. If we wish, we can then mentally pretend that this logical Z operator extends along here. And having done so, we then start measuring more stabilizers. And this then allows us to error correct a bigger version of the same logical qubit. So no extra information, it's just a bigger logical qubit. It is actually technically a worse logical qubit because in this case, the logical operator is longer and there are more opportunities for failure. So we haven't made things better yet, we've just made it longer. So why would we do that? Because we can make it shorter again. And after doing this expansion and contraction process, we've now moved our logical information. And graphically, that looks like this. So we started off with information in one place, expanded it, contracted it, and moved it. So once you get comfortable with that, you stop worrying about these details and just start drawing diagrams like this. And then things get a lot more fun because we can draw things like this. So here is an example of a logical move. And, you know, at the abstract level, software level, whatever level you wish, we forget about all the details of initializing individual qubits and measuring them out and just draw lines. And you'll notice I've deliberately drawn this line such that it curves back in time. And that's not a mistake. That's not invalid. This is also not a special feature of the surface code. Once you get happy with these figures, you'll see that this U shape represents creating a bell pair. And this is then the remainder of a teleportation argument. So you can do this trick in any code. It just happens to be kind of pretty to look at in the surface code. Furthermore, and another thing that should be emphasized, you can really do this. You can then put clipped circuits here, and then you can run C0 gates, Hadamard gates, S gates, any combination of all of those things in effectively zero time as seen by the algorithm. It takes up space-time volume, but in terms of the actual algorithmic progress, you can always do these things offline. And again, I stress this is not a property of the surface code. It's a property of quantum circuits. It's very handy. And it means that whenever anyone asks me, oh yes, but how long does it take to execute a C0 gate in the surface code? The answer is 0. It doesn't take any time. You can do it in space-time volume offline ahead of time.
Hey, Austin.
Yeah.
It's Cody here. There are a few questions, and I'm thinking this is a good time to pause and ask you some of them.
Absolutely. Go for it.
Okay. So I think actually going back early in the talk, there's a question that says, you know, what is this graph representation of the surface code? What are the black dots? What are the white dots? Do the axes matter?
Okay. So let's go all the way back to where this was first defined. It's this graph, yes? Or even further back, this graph, yes? I think black and white
let's
dots
go
must
ahead
have
and
been this
start
graph.
with this one. Yeah.
Okay, so every single one of the dots is just a qubit. The coloring is only what are we using it for at this point in time. So we're going to call the white qubits data qubits. We're going to call the black qubits measurement qubits, but it should be very clearly stressed they're physically identical. So we're going to use each measurement qubit to interact with its 4 neighbors to measure a stabilizer using circuits of this form. If we're finding X errors, it's this circuit. If we're finding Z errors, it's this circuit. Okay.
Hey, Austin, can you define the plus and minus symbols?
Yes. So this was, I mentioned, for physical reasons on a superconducting process, this is a plus y/2 rotation and a minus y/2 rotation. So they're equivalent to the Hadamard. If you prefer, just mentally replace both of these gates with H.
Yeah, and just for like clarification, because people have been asking about axes, on the left diagram, that's a top view of the device, like, or schematic of like what it would be like to look down on the device.
Correct.
And the right is a diagram where time is moving from left to right in a circuit.
That's right. So yes, if we chose this particular qubit, first you initialize this qubit, then you do the plus or Hadamard gate on this qubit. Then you start interacting. So this one is with the number 1 qubit, all right? And then you interact CZ with number 2, then the 3, then the 4, Hadamard or minus y/2, and then finally measure this particular qubit. So that's all the action occurring on this particular measurement qubit. And all of these things then go in parallel. So all of these circuits are implemented in parallel. Any more questions?
Okay. Yeah, there were a pair of questions about detection events and boundaries. So one question, I'll read both, they're related. What happens to the detection events at the boundary? And then maybe a little bit more finer question, why wasn't there enough information the first time boundary in this example?
Okay, so here is an example of a detection event at the boundary. We explore, we hit the boundary, we match it to the boundary. And you can see that what we do is we say, well, given this is the single isolated detection event we have at the moment, our most likely belief of what error generated it is an X error on this qubit. And then what was the other half of the question again?
Why wasn't there enough information in the first time boundary?
So here is an example here of a situation where we don't have enough information. So the reason there's not enough information is, for example, we don't know what's going on in this round yet. If we find that there's a detection event here, we'll match this to here, all right? So we can't keep exploring yet. We don't have any more data to explore into. If you like, there's no graph to explore into. We cannot uniformly explore in the graph when the time boundary is there and there's no data. Any other questions?
Yeah, there were a couple of questions about correlations. So for example, on correlated errors, what are B and C? And then a related question, what's the difference between A, B, and C?
Sure. So A is our good old surface code. We're still just measuring X stabilizers and Z stabilizers, no difference there. So as before, the X stabilizers are the dark ones, the Z stabilizers are the light ones. What we do then is we perform an analysis similar to the repetition code analysis we did before, but now this is a fully 3D graph. These representations are just 2D slices through that graph. If you wanted to have a time axis, that time axis would be out of the page towards you. So this is a top-down view of what is really a 3D graph and just a single slice. So over here, we have the graph corresponding to X stabilizers. All right, so you see it's 3 wide and 4 deep, 3 wide and 4 deep. X stabilizers detect Z errors. We have a Z error. I know it's a Y, but it contains a Z error. And that triggers a detection event here on this X stabilizer. This graph here is associated with our Z stabilizers. So again, we have 3 high, 4 wide Z stabilizers, 3 high, 4 wide Z stabilizers. We've built the graph of where errors will get detected. And again, to stress, this is just a 2D slice of what is really a 3D graph with time coming out of the page in multiple layers. But nevertheless, you can still then see here's a Y error, which contains an X error, which triggers 2 Z stabilizers here. Knowing that, we can match these, knowing that there's a correlation, Y errors introduce correlations between this graph edge and this graph edge. After matching this, we can reweight this edge to have a 50% probability, a lower weight, which means the minimum weight perfect matching algorithm will preferentially choose to match this direction along the chain and correctly identify it.
So Austin, there was a question. It says, what does it mean to run into the edge? And I believe that might be in the context of boundaries.
Sure. So I think this is still a good example of that. So here we are going to say that this detection event should be matched with this boundary. And fundamentally, you basically say, well, we're going to, in software, insert a Z correction here and a Z correction here. So I mean, what is a boundary? If you have a look at this particular X stabilizer right here, just this one right here, a boundary is a place where a single error can occur, this Z error, leading to just a single detection event. That's the definition of a boundary. Single error can lead to a single detection event. And it's nothing special. It just means that if we get a single detection event, then we connect to the boundary, which is this way, and we put that single correction here. So it just allows you to distinguish between this error, which leads to one detection event, and this same Z error here, which leads to two. And in this case, this one gets cancelled and you have a chain and just a single detection event at the end point of that chain. And it's worth elaborating that in general, a detection event always occurs at the end point of a chain of errors. So you have a bunch of detection events, which are themselves endpoints of chains of errors. And the game is then to go and try to find those chains of errors. And you use the minimal weight perfect matching algorithm to do so.
So there is another question related to boundaries. Why is it that the boundary of the code seems to skip stabilizers? Example, at the right, oh, sorry, my screen just sort of moved. Example, at the right edge of the code, there are only 3,4 stabilizers, and at the bottom, there are only 1,2 stabilizers, and so on.
Let's see, what slide would that have been in relation to? So here, obviously, it's more uniform.
Yeah, I think it's probably one of the earlier slides where you're giving the order of the 2-qubit gates. And it's referring to weight 2 stabilizers.
Okay, it's probably the, yeah, I understand. So it'll be looking at this one, for example. So we have weight 2 and weight 4 stabilizers in this particular picture. So there is a difference between this picture and the one that we focused on in the correlations. Indeed, this one has weight 2 and weight 4. The other one has weight 3 and weight 4 stabilizers. So the reason for that is not complicated. The lattice has to end somewhere. If we had more qubits here along this line here, well, then this would be a weight 4 stabilizer, but they're not there. There's nothing to measure. And so we only measure what is left. So, you know, when you take your 2D array of qubits and you cut out a piece, on the bulk, you'll have weight 4 stabilizers. Around the boundary, you'll have weight 2 or 3, depending on how you cut the surface out. So you have to cut through stabilizers to cut out a square of qubits. So looking at the other one, you'll notice that this is a different way of cutting a 2D grid of qubits out of a bigger piece. And in this case, we're cutting off, for example, a data qubit here to make that cut. In the previous picture, if you wanted to really push things, you would find that the cut goes along like this. And then we sort of have a zigzag waffle cut to actually get those stabilizers out. But yes, all because of the way you cut it out. Any more?
There are a few questions around moving qubits. So
yes.
Let me see. So first of all, what is the purpose of moving logical qubits around?
Okay, great question. So when you run an algorithm, you frequently want to interact logical qubits that are not necessarily sitting next to each other waiting to be interacted. So this helps with, I mean, if you've looked at any quantum circuit for any algorithm, you'll see that almost all of them require long-range interactions. So this gives you a way of doing long-range interactions. Very handy. And really that's the only real reason. You need to be able to do long-range interactions in a logical algorithm.
Okay, so on an image such as this one for the logical move, how is time represented?
So this is this up arrow. Time's going up, and you'll notice that this basically represents a qubit going backwards in time. That is valid. You won't know the full state of the logical qubit so teleported, but you'll know it up to Pauli operators. So provided you only plan on doing Clifford things to it, you can really do this. As soon as you want to do a non-Clifford thing, like for example, if you wanted to do a T-gate or a Toffoli gate, you would need to wait until after this horizontal time, so actually knew what the full state of the qubit was, up to byproduct operators.
So 2 questions that are related. What is the purpose of expansion and contraction? And then how do you know to make the qubit bigger, and why do you want to do that?
Okay, so the purpose is so you can actually do this movement of the logical qubit. Here's an extreme example of expansion. So this underside would start off life as a great big sea of zeros, and then you would start measuring. So this is a great big expanded logical qubit, and then at the end you would contract. So the purpose of expanding and contracting is to allow you to move logical qubits. And the other half of the question, when would you do that? When the algorithm dictates that you need to do an interaction between logical qubits that are not local to one another.
Well, and the question was, why would you change the size?
So I guess that's inherent in just the fact that when you move it, that qubit becomes bigger. It's really a statement that if you focus on this vertical part of the qubit's life, the logical operators are fairly short, all right, which means there's only so many ways that errors can cut across them, which means they're fairly robust. Whereas if you focus on this time period of the qubit's life, that logical operator extends all the way along here, meaning there are many potential error chains that cut across this. Now, this is not a big deal. If you go back to the simulations, you'll see that it's this formula per time slice. Well, you can also think of that as the reliability per spatial slice. So you just count how many slices there are along this thing, and that will give you the reliability of your information for its entire space-time journey. You don't get anything for free. You make a big, long logical qubit like this, you can get errors along this length as well. And you have to use that formula to estimate the total probability of error during that journey. Any more?
So this question might be a little more subtle. What are the implications of a logical move? How does one location in space differ from any other location?
In an ideal computer, they're physically identical qubits, so it's only done for algorithmic purposes. You would move it just because the algorithm says, hey, now we want to increase this qubit with that qubit, and so on. So physically, it should be identical.
Okay. Another question about movement. Does this mean that moving logical qubits around is quite robust to noise, even across far distances?
That's correct. So again, you use that logical error per slice, which is both time and space. And clearly, if you go 10 times further, you're going to accumulate 10 times the error that you would have otherwise. So, you need to essentially look at your algorithm, work out the total path length of all your logical qubits journeys, and then choose a sufficiently large code distance so that the probability of failure in all of that volume is low enough for your tolerance.
So here's a question that probably is about this diagram. In the logical move graph, does this mean time is reversing at some point?
It doesn't mean time is reversing. I mean, if you imagine how this would really look in a quantum computer, time passes vertically. So let's imagine this was the actual beginning of the life of the logical qubit, for argument's sake. So it's initialized here. Well, before this even happens, we're going to initialize a bell pair over here. We're going to store the two halves of that bell pair for a while. We're then going to initialize, and there'll be two separate locations for a while, and then we're going to create this big band here. So time passes vertically, and slice by slice is what the computer is actually doing. So no reversal of time. It's really just creating a bell pair and then measuring it out, doing teleportation.
Okay, and I think just a point of clarification, the z-axis is time. Are the x and y just spatial x and y directions?
Exactly. So yeah, this plane is your sea of qubits executing a particular logical algorithm, this pathway and all of its stabilizers in software.
Okay, another question that is perhaps a little bit subtle. Is this figure related to defect-based surface codes?
It is not. So this is lattice surgery. So defects dominated for a long time. That's how estimates of all kinds of things were done for a long time. And then we discovered that lattice surgery, when you work at it, is actually significantly lower overhead, about 3 to 4 times lower overhead. So yeah, defects at the moment have been deprecated in favor of lattice surgery. This is a single pipe that represents a logical qubit stored on the inside of the pipe. If you've been looking at defect diagrams, you would have cuts in a larger space-time, pairs of them, and the logical qubit would be associated with the exterior of those double cuts. Here, all the information is inside the pipe.
Okay, another question on movement. Can we just move one step at a time and then turn off the old position? Is there any
Yes.
reason we want to turn on all the units on the route and then turn off?
Just you get there quicker. I mean, if you did what the question suggested, it just means you would move slowly diagonally from one place to another. And if that was the available space-time in your algorithm, keeping in mind, there are supposed to be lots and lots of logical qubits doing their spaghetti thing all over the place here. It's certainly conceivable that the only pathway you have to get from one place to another is this kind of diagonal path. Yeah, you could do that. Most of the time, when I imagine writing software to actually do this, you have nice rectilinear paths because that's just easier for a human to program. But yes, you could definitely make more fluid paths if you wished and go diagonally in space and time. No problem.
Okay, and maybe something clarifying how movement works. Does moving long distance require qubits to have very high coherence times?
No, so it's exactly the same type of qubit everywhere. Doing the surface code requires fairly modest coherence times. So, that ballpark figure you're shooting for is 10 to the minus 3 error. So your coherence should be at least of order 1,000 times longer than your gate time. But by any reasonable standard, that's not an excessively demanding task, keeping in mind that no one's done it yet, but still, it's well within reach. And no, the qubits along this path are no different. You are just accumulating error as you go along this path at exactly the same rate as you accumulated error as you went along this vertical path. With maybe some caveats for the fact that in some architectures such as our own, measurement is fairly error prone, and that can actually make some directions, such as the time direction, weaker than a space direction. So in some architectures, including our own, you actually may be more robust per spatial slice than you are per time slice. But that comes down to the details of the architecture. Generally speaking, it's symmetric, and you just can use the same formula everywhere for the total length.
There's a question, are these 3D block diagrams documented anywhere further or just something used in the field? Do they have a name?
So this is a way of representing lattice surgery. Yes, I'll have some links later on papers that describe this in more detail. If you want to be really technical in those papers, they'll say that these long prisms here actually are not there. All right, they're only there for the human being. And the reality is that in software, you remove them, and the only thing you see is the cubes. You don't do that for a human being because then you can't see what's going on. Everything is tightly packed. I'll show some examples of tight packed diagrams later. So yes, there will be links. Yes, this is all explained elsewhere. But for the moment, hopefully it's clear that this just represents the movement of logical information.
Okay, there were a few questions that I think we'll also just make sure we cover for terminology. So what is rotated distance?
So when you have any surface code, you're really counting the distance as the shortest path across it. So here's a good example of distance. You have 1, 2, 3, 4, 5 qubits involved in the logical operator. It's a distance 5 code. This is an example of a rotated surface code and an example of how you calculate the distance of that code. If we went back to the unrotated codes, this is an unrotated code. It's very similar. You go and get your logical operator, which would be a vertical line, for example, down here, and then you count 1, 2, 3, 4. So this is an example of a distance 4 unrotated surface code. So the distance is the shortest possible chain of errors that equals a logical operator. It's the definition in any code. And in a topological code, it's very easy to calculate because you're looking at basically the diameter of your patch. And
okay, what's the repetition factor for the surface code?
As in how many times you need to repeat the stabilizer measurements to do things?
I don't have any more context at the moment.
So Generally speaking, for a distance decode, when you move things around, you need to repeat things d times. So for example, if we look at this picture, the initialization happens once, but the measurement of destabilizers occurs d times. You need that d number of repetitions because, all right, in here, there is a logical X operator, and we want to move that logical X operator to here. To do that movement, we multiply by a bunch of stabilizers, all these ones illustrated in blue. To do that movement and actually have any chance of getting the right answer after movement, we need to know those stabilizer measurement values well, and that means we need to repeat them of order d times. And I'll say of order d times because, you know, in our architecture we have low fidelity measurement, and so you could imagine that might actually be a little bit bigger. So you have unequal shaped prisms. I can easily imagine these things will actually need to be a little bit higher than they are wide in our hardware. But if we didn't have that asymmetry, hopefully the repetition factor that was referred to is how many times d times, so that you have reliable movement of logical operators along these pathways.
Okay, there were a couple of questions about sort of fundamental properties of surface code. So first, can this code handle a linear combination of X and Z errors?
Yes. So here is an example of a linear combination of X and Z errors. So it can handle quite a density of errors and still reliably correct everything. So here's an example of many errors. And while this is just an example of one type of error, you have two separate graphs to handle the two types of errors, plus correlations between those errors that allows one type of correction to give hints to the others. So yes, you can cope with very general random scatterings of X, Y, and Z errors.
Okay, and another question, can you ever have a logical Y operator with qubit count, i.e. the Y distance of the code, smaller than 2D minus 1, where D is the distance?
A logical Y operator. I mean, there is a logical Y operator in these pictures. It's just the diagonal, for example. If you put a chain of X and Z errors on top of each other down the diagonal, you get a logical Y operator. And in these codes, the logical Y operator is also designed so that it has minimum distance D. So in this particular code and all the codes we're dealing with, the code distance or the minimum length of your X, Y, and Z logical operators is all D. Now, the question was, can you make that Y operator even longer? Not really, because if you have a logical, well, I won't say it's impossible, but in these codes, you can always do a diagonal logical Y operator, so the logical Y is always the same length as your logical X and Z. If you couldn't do diagonals by some magical property, then yeah, you could imagine that the logical Y operator is even longer, but that's not the case in our codes because of the diagonals.
Okay, so back to Y errors versus linear combinations. How is the handling of Y errors different from the linear combination of X and Z?
So we need, from an algorithmic point of view, to handle them not directly. So if we just focus on this Y error, just one Y error in isolation, that Y error would lead to 4 detection events, all right? And we want a graph. This would be a graph with a hyperedge if we put it in directly. So instead in software, what we do is say, well, we can't handle a single error that leads to 4 detection events directly. Let's instead look at it a bit more carefully and see if we can break it into pieces. And of course we can. We can break that Y error into an X error and a Z error, each of which leads to a pair of detection events, which then forms part of a graph. And then we put back the fact that it's a Y error by correlating this edge with this edge. Can you, in principle, deal with a Y error detected directly? Yes. There are maximum likelihood algorithms that do this. They are very expensive exponential runtime algorithms. Do I expect that there's an efficient way? Well, no. But hey, if someone wants to give it a try, please do. So right now, I will say that the limit of our imagination of how to handle a Y error efficiently involves breaking it up into pieces and then hinting at its true nature through correlations. Maybe you can do better. We haven't thought up a way to do so.
Okay, so there's a question for clarification that actually goes back to, I believe, one of your classical processing slides. And the question says, so the green dots are the measurement qubits, and that's why they're in between the qubits in the picture.
So in this picture, we're looking at a graph. So yes, if you wish, these green dots correspond to where the measurement qubits would be. And so that's correct. I think I'll just say, yes, that's correct. Technically, a detection event is associated with a measurement value change, just for language purposes. Yes, it's a measurement on a measurement qubit, and these green dots are not themselves measurement qubits. They're indications that in this time sequence of measurements, that measurement value has changed. But yes, you could write the existence of an extra measurement qubit between each one of these data qubits.
So there's a follow-up question, and I think it's referring to the first slide in this series, which is maybe number 7 or 8. The question is, in that initial case, how did you know which qubit was the likely error source? Couldn't it be the first or second qubit?
Well, for it to be the second one, there would have been a second detection event here. So if there had been 2 detection events, yeah, sure, you would have matched them together and you would have said that the error was on this data qubit. But because there's only one in isolation, the most likely explanation is this matched to the nearest boundary and a single correction on this data qubit. If you put a correction on this one, that would create detection events here, which are not present.
Okay, thank you. I think we've addressed a lot of questions. There are a few remaining that are kind of more discussion in nature, so we'll try to loop back to those at the end of the talk and give Austin an opportunity to finish his slides.
Yeah, no worries. And thanks for all those questions. That's great. The more the merrier. Bring it on. All right, moving on. So we've talked about movement. Now, what else can we do? So one very cheap thing you can do is you can just apply the Hadamard gate to all of your data qubits, and this does logical Hadamard. Why? Because if you apply a Hadamard to an X operator, it basically transforms it into a Z operator. So you exchange your logical operators and implement logical Hadamard. There are some issues in terms of the fact it's also going to change your stabilizers, but that's not really a big problem. You rotate your data, but hey, you've exchanged your logical operators and you're done. You can also do a much more complicated thing, the details of which I won't talk through. So it was originally proposed by Ben Brown and others in this paper, and our own Craig Gidney created a realization of this S-gate. The takeaway message is you can also do a logical S-gate, so this phase rotation. It doesn't require a very great deal of volume, more than the Hadamard. You can see, instead of just being a single time slice, we really have 4 of these D by D by D cubes that implement that gate, but still, that's not that much. So we have a low overhead S-gate as well in the surface code. And what else? We have these ZZ logical measurements. So if we start with a pair of logical qubits, and we want to measure a ZZ logical operator, multi-body logical operator, we can do so. We firstly can close up the code to create a uniform sea of stabilizers between those two things. And if you think about what the product of all those stabilizers is, well, it is precisely the remainder, this logical operator and this logical operator, because all of the Z's in between cancel. This stabilizer and this stabilizer share a qubit here, they both touch it with a Z operator, those operators cancel, and so on through this whole sea. So again, talking about how many times you repeat this of order D times so that these measurements are known. After doing so, you have a good, robust, fault-tolerant way of measuring a ZZ logical operator. And as I'm sure you can guess, the next thing that you can also do is a logical X measurement. It's practically identical, apart from the fact that you close up in a way that is perpendicular to your logical X operators. Fantastic. But what can you do with logical ZZ and logical XX measurements? It's not obviously that that's very useful. Well, it turns out they're very useful. So you can create CNOT gates using just logical XX and logical ZZ measurement. So here is the explicit circuit that really depends in no way on surface codes or anything. These are just straight out measurements with their classical corrections. And then here is the physical realization of that. So here are your control and target qubits. And then we're actually doing the XX measurement first, and then the ZZ measurement here. So you might then ask, well, what about a single control multi-target? What would that circuit look like? Well, you end up with just having to expand this part. So we would need, if we wanted to do that, a multiple logical qubit XXXX operator measurement. And can we do that? Yes. Any number of logical qubits, if we wish to measure any combination of X and Z, we can do that. It's a matter of creating sort of a connector piece between those, and then you can measure whatever operator you wish. And that is really useful, not just for single control multiple target CNOT gates, but if we then move on to considering state distillation, it becomes a very, very powerful technique indeed. So here is a great big circuit, which we're going to talk through in a bit of detail, that does state distillation. What does that mean? It means we want to create a state 0 plus e to the I pi over 4, 1, and we want to make it robust. And so how do we do that? Well, step one, let's just focus on this little piece of the circuit, not the whole thing, just this piece of the circuit. So what is this piece of the circuit doing? We get a plus state, so this is 0 plus 1, single control multi-target CNOT gate. So we know how to do those. This is going to create the state 0, lots of zeros, plus 1, lots of ones. It's going to create a cat state. So let's think about what those things are for a little while. So here is such a state. Lots of zeros plus lots of ones. This is the +1 eigenstate of the lots of x's operator. Great. And here is also a -1 eigenstate of the lots of x's operator. Also great. Now, what's special about that? The special thing about that is that the all zero state is the sum of these two eigenstates. The +1 and -1 eigenstate of the lots of x's operator is precisely the zero state. Okay, great. Why is that good? That's good because if we then go and measure this operator, what's going to happen is we're going to project the all zero state into one of these two, either of which will be good enough for our purposes. So we'll either get the result +1, in which case we have exactly this state, which is exactly the output of this circuit, or we'll get the minus version, which whatever, it has a Z operator in here as well, which we can track, and we've implemented the circuit. So you implement all of that using just a multi-body X operator. And here is an example of the fatter notation of lattice surgery, which is more close to what is really going on in the hardware. For visualization purposes, we frequently take these thin connector slices and then expand them into larger prisms. It can make life easier. But here I've treated you to the expanded version just for visualization purposes. So these 16 bricks here around the outside correspond to these 16 qubits going up here. So you'll notice there's 4 that are not touched, 4 that are not touched, another 4 that are touched, another 4 that are touched, 3 more around the corner that are touched, skip 1, and then the final one. So this is a physical realization of an 8-way multi-body X measurement that implements this first part of the circuit. Very, very compact. Moving on.
Hey, Austin.
Yeah.
For this circuit and what you're describing here, there's a question. In the distillation protocol, are we encoding a cat state and then applying T gates?
Yes, and I'll discuss that in more detail. First, I'm just focusing on the realization of this part of the circuit. But yes, that is the flavor of where we will get. So moving on for the moment. So layer by layer, you can implement each one of these single control multiple target CNOT gates using multi-body X measurements. So this is 4 layers of multi-body X measurements, and that prepares this state. This state is a logical state. It's the logical 0 state of the Reed-Muller code. That Reed-Muller code has a very nice property that it has a transversal T gate. And we're going to use that in a moment. But for the moment, we have the logical 0 state of Reed-Muller code right here. We also have a logical plus state. right here. And then what we do is going to do a controlled logical bit flip. And when you do a controlled logical bit flip, you end up with 0 and 0 together and 1 and logical 1 together. So that's the controlled logical bit flip that takes us to this line. Now you have a bell pair, but you have a bell pair between a single logical qubit and 15 other logical qubits that are prepared in a logical state. So here's our bell pair, crazy, complicated bell pair. But it's a very good bell pair because 1/2 of it is the Reed-Muller code, which has transversal T. Technically, transversal T dagger leads to a T gate, but hey, who's counting a dagger? So if we apply T dagger, we will get the T, this bell state, and then we do a logical X measurement to get rid of that Reed-Muller code. That will introduce a random phase flip, which we can deterministically work out from the parity of these measurements. And we're left with our T state up to a known parity, which we get from classical processing. So I hope that took care of the earlier question. So this is the full picture. And then you can actually build that. Now, there are some details in this figure that we're not going to talk about. Each one of these little red blobs is injecting a state, starting with a single physical qubit, turning it into a small logical qubit, has a 50% success rate. So this cluster of injections is really keep injecting until it succeeds. In this case, succeeds with a probability of failure of 1 in a million, because there are 20 attempts, each with 50% chance of failure. Having injected our T state, we then use this structure to do either a T or T dagger gate. So these guys are probabilistic. 50-50, you get T or T dagger. Then finally, there's this green blob. This green blob is the gate that corrects for a T when you really wanted T dagger. So they're only included 50% of the time. And in particular, what I wanted you to take away is there's this gap here, this vertical gap here. This vertical gap here is only there to give yourself enough time to do the classical processing. So classical processing is an integral part of doing this. Until you have all your error correction up to date, you don't know if you need to apply that S gate or not. So a critical component of a computer that runs quickly is very fast classical processing. Anywho, takeaway message is this is state distillation. I hope you can see that it is not a very big circuit. I mean, it's big-ish, but it's not enormous. And in particular, if you compare it to just the cost of moving data from one place to another, just movement can rapidly become the same cost as one of these distillations. So in the modern era with lattice surgery, distillation is still significant cost, but it's no longer the majority cost of an algorithm. Craig Gidney worked out for even Shor's algorithm, which requires a lot of distillation, it's only about 25 to 30% of the total space of the computer these days, down from peaks at 99 plus. It's really not the biggest cost anymore.
Hey, Austin, while we're on the slide with the circuit, what's the reason behind the design of this circuit? How do you decide which qubits are the targets of multi-qubit controlled X gate, and how many of those do you need?
Okay, so that is this circuit question. All right, so this circuit creates a code, right? The desired property of that code is a transversal T gate. Now, how do you achieve that? All right, so if you just look at these 15 qubits that are going to form that code, what we're going to do is we're going to create a superposition of computational states that for logical 0 have either no ones in them or 8 ones in them. All right, so all this state here that has a whole bunch of zeros, after executing this part of the circuit, we'll have a superposition of all zeros and 8 ones on these 8 qubits. When we introduce this bit, it's going to modify some of the states, but it's always going to leave 8 ones on those computational basis states. So when you're done, you will have a superposition of 16 states, all of which have either all zeros or 8 ones. Why is that important? A T gate is 1/8 rotation, and that means that when you apply a T gate to that logical 0 state, all the phases cancel. So that's the logic behind the construction. Vice versa, When you then perform this logical bit flip, you'll see that this logical bit flip has 7 targets. You transform what used to be all zeros plus computational basis states with 8 ones into a state that is all ones plus states that have 7 ones. So then you have either 15 ones or 7 ones in your computational basis states, 1 less than 8, and that makes the transversal T into a logical T gate. So hopefully some people can follow that, but it comes down to building computational basis states that give you the right transversal application of T. Any other questions at this stage?
I think we'll let you finish, and then there's a few discussion questions we can cover at the end.
Sure. So at this point, we've stayed firmly in theory land, and here on example is a multi-layer distillation circuit just for eye candy. So what do we have so far? So physically, it's 2D nearest neighbor architecture, which is very desirable for many solid-state implementations. Modest fidelity requirements. We have the ability to do very compact universal computation with arbitrary range interactions. You also see on the right an example of the flexible code strength. So if some parts of the algorithm require more error correction than others, as you can see in this diagram, well, you just make them bigger. So it's a very, very flexible code. So if we now agree, well, sounds great, let's build it, what does that really mean? What additional challenges do you hit when you try to build it? So we're now going to talk about the current status at Google in the lab. So we're focused on 72 qubit devices. And what we really want to do is get that holy grail of quantum computation, which is prove that as you get bigger, things get better, which is currently not true. We need to get our qubits better to prove that. So the goal is bigger is better, continuously running. So generally speaking, when you turn on your computer and start running it, things can heat up, other things can happen, leakage can accumulate. We want to be sampling from the steady state of the computer, whatever that may be. We also want to decode in real time. We don't want to be cheating using some maximum likelihood offline decoder. It really has to keep pace. And we also want to prove that we have extreme exponential suppression. So if you imagine putting a repetition code on this, well, you can put a distance 34 repetition code on such a circuit. We want to show that you get extreme exponential suppression of both bit flips and phase flips all the way out to distance 34. So when you do that, what stops you? Or when you try to do that, what stops us at the moment? Well, firstly, when you build a chip of this size, it does not work. So that's probably one of our biggest challenges right now. Some of the couplers, some of the qubits just don't work. The other thing that limits you is with a chip this complicated, it gets very difficult to achieve very high coherence. So we're limited around the 20 microseconds level. In our dreams, we'd love 5 times that. So we could get really, really good gates. So that's a big challenge, making something so big, so reliable, and so clean that you get 100% yield and high coherence. Very challenging fabrication problem. Our readout and reset are slow at the moment. So 1 microsecond is slow, particularly relative to our 1 and 2 qubit gates, which are typically sub 20 nanoseconds. And during that amount of time, you can imagine you accumulate quite a lot of error on your poor data qubits that are sitting around waiting to do something useful. When you try to calibrate a system this big, there are a lot of challenges. Firstly, when you fabricate it, not all the frequencies of the qubits are what you tried to fabricate. So there's quite a bit of drift between design and actual realization. Also, these qubits need to be able to be tuned over a large frequency range. So we operate in the range of, say, 3 to 8 gigahertz. And for some of our gates, we need to tune the frequency of our qubits over a gigahertz. So they need to have a very clean performance over a large range of frequencies. And what you'll see happen is that there are some frequencies, sometimes quite wide bands of frequencies, where they just don't work very well. And those bands need to be avoided. And when you have this much hardware, all with unique spectra with different notches that perform poorly, it's tough to choose operating frequencies for everything such that everything can talk to one another, implement good gates. So calibration limits us also to modest gate error rates. We'd like, again, to get another factor of 5 lower than that. Another big one, which you can read about, so all of these things are published, is constant grace. Right now, we have a chip operating around 10 millikelvin. superconducting, and it's really cold. And if a cosmic ray hits it, it heats it up quite a lot, and that ruins everything. So, you know, at the moment, a cosmic ray strike on our chip for tens of milliseconds completely randomizes its performance. So there are a number of hardware fixes that have been proposed to mitigate that, to localize the heating and get the heat and phonons and quasi-particles out of our system as quickly as possible. But it should be stressed that this has to be mitigated at the hardware level. You can't just randomize all your qubits for hundreds or thousands of rounds of error correction, expect there to be anything less left when you're done. So this is a big challenge. We also need to get the coding as fast as the computer. So superconducting qubits are great, nice and fast, but that then becomes, for the classical people, such as myself, a software challenge to actually write software that runs as quickly as the hardware. So there's a lot of work to be done, and that gives you a snapshot of what struggles we're currently up against to get to this next milestone. If we start looking further into the future, you have to ask yourself, well, here is a superconducting quantum computer. Is this really scalable? And the short answer is, as pictured, no, this is not. Yeah, there are thousands upon thousands of SMA connections that you have to make reliably for this to work. And, you know, all of this needs to be changed as things grow to really have any chance of scaling this up. So to give a crude schematic of what that might look like, this is now a slice of this. So here we have a round fridge, this yellow object containing wiring and a chip at the bottom. Here we have a slice of a fridge containing a chip at the top, wires coming down and then fanning out to the control electronics. These would need to be made multiple coax to control electronics out here. And the whole point here is that if we can get aboard a 10,000 qubits up the top here, with all of the electronics to drive them all in a 10 centimeter thick slice, you can then imagine scaling this up to a bigger computer. So this is what our current vision of an order 1 million qubit computer would look like. Great long fridge, linear chip made of multiple sections, and all your control electronics filling a very large building in a kind of Noah's Ark style design. So what does that mean in terms of theory? Well, it means that you're not going to have this 2D sea of logical qubits. You're much more likely to have a 2 by n design of logical qubits. You have to design all your algorithms to work in that regime. And hopefully what all of this theory in this talk has convinced you of, that's really not a problem. Provided you have a double layer of logical qubits, you can certainly move anything past anything and build circuits that do state distillation, whatever it is that you want with that constraint. So there was an earlier question about more details. Here's a bunch of references that will give you more details on lattice surgery and those kinds of 3D diagrams that represent that. And of course, I'm happy to take any questions.
Okay, so there are a few questions that are a little bit more discussion in nature. I'll combine some of them. So are superconducting qubits the best choice for the surface code? And can you comment on other physical systems such as trapped ions, neutral atoms, etc.?
Sure. So I think they are the best. Otherwise, I wouldn't be doing what I'm doing. But of course, if you talk to other groups that work on ion traps, they'll say there's the best. So what are the pros and cons in a kind of as open and honest possible manner? So ion traps are slow. Fundamentally, that's the reason why I think the superconducting qubits are better. You're talking gate times that are orders of magnitude slower, measurement times, cooling times that are orders of magnitude slower. So while I would certainly say there is the potential, possibly, to get higher fidelity gates out of an ion trap, maybe. Scaling that up and making it a fast, high performance computer, I think will be very challenging, particularly if you start going from one ion trap to another using photonic links. Just the sheer speed of the computer, I think, will suffer so much that that ceases to be practical. With superconductors, you have other challenges, all the ones I listed. Cosmic rays are a big one, all right? You have to ask yourself, how are you going to isolate the computer from that? As I mentioned, we have ideas, but that's a big challenge. We like the fact that it's a fabricatable technology, which we feel will allow us to scale up more easily. We also like the fact that it's a big technology. A superconducting qubit is of order a millimeter center to center. So when you look at these diagrams, you might think, oh, this is microscopic. Well, no, not really. The distance from this corner here to the center of this is of order 1 millimeter. This is big. You might say, well, surely that's bad. The answer is no, this is actually really good, because the only way you can imagine getting all of the wires out to all of the necessary control electronics is if your qubits are big. If our qubits were a factor of 10 smaller, it would be difficult to even imagine what a large-scale computer looks like. So I guess the fact that we feel we can draw a diagram like this makes us confident we're on the right path. I am yet to see an equivalent picture that would have similar performance with ion traps. And I'm careful here because, I mean, there are speakers here that also work on ion traps and they do great work. So, you know, I definitely feel that these are both great things to work on. I work with people that work on ion traps. I've proposed architectures with ion traps. But the number one thing I come back to is speed. I'm concerned that long term, if we can get a superconducting computer to work, then the speed of that computer is going to say that the ion trap approach doesn't work. Now, where do I think ion traps shine? Because you're dealing with individual atoms, I think there is the potential there to get much higher fidelities than we probably ever will. Furthermore, you can get arbitrary interactions out of a group of ions in a single trap. So for short-term applications, if we find something to do in the NISQ era without error correction, I think ion traps have an excellent opportunity to be the thing that does NISQ. Whereas with superconducting qubits and only nearest neighbor interactions and perhaps not the highest fidelity gates in the universe, I suspect we're at a strong disadvantage there. So, you know, horses for courses. Ion traps, I personally believe, are the way to go if you are focused on no error correction. My personal feeling is that superconducting, the speed of it, the locality of it, the compatibility with the surface code is the way to go if you wish to do a large-scale error-corrected computer.
Okay, so related to physical implementations, I believe this is a question related to physical gates, and it says, aside from wanting to limit noise, is there any reason for not using higher qubit gates?
So multi-qubit gates, I assume, is the reason?
Yes, I believe they're referring to more than 2 qubit gates.
Sure. So noise is really the answer in 2 ways. So firstly, it's difficult to do a multi-qubit gate with high fidelity. So you have to ask yourself, is my, for example, one measurement qubit that wants to touch 4 data qubits in one hit, and there have been proposals to do that. In ion traps, they even can do these things and have done these things. Is the noise of that gate really lower than the noise you would get from the 4 individual ones? And in our particular case, we feel the answer is probably not. It's probably better to do the individual ones. Secondly, even if you can implement that gate and do it with good fidelity, the fact that you're doing it at all introduces additional noise possibilities. So you're coupling a group of 5 qubits now, and it's reasonable to suspect that at the very minimum, any arbitrary pair of those qubits can now flip. And that's a problem for the surface code. Let's imagine we focus just on this central 5, and now we're going to do, say this group of 5. So we have a measurement qubit here and 4 data qubits. And we're going to measure the stabilizer in a single shot. It's very reasonable to expect that if you can do that, then it's possible, for example, for this data qubit to flip and at the same time this data qubit to flip. So you get 2-body noise during that gate as a minimum. And you get 2-body noise on pairs of qubits that degrade the code distance. So we don't feel you would win at all. Dividing this up into carefully ordered 2-qubit interactions, both in our case achieves a high fidelity of the total operation, plus limits the creation and coupling, leading to noise that would degrade the code distance.
There's a couple of questions related to the performance of surface code. So first, what is the typical threshold for full chain measurement efficiency for the surface code? And then I think a related question was, it says the decoding paper you give was published in 2012. Is that still state of the art?
So the decoding paper in 2012 is pedagogical. So that was why it was chosen as the reference. Is it state of the art? No. Is the full state of the art published since we're at Google? No. So, you know, we certainly have some very good decoders internally that are not public, but they don't work in a fundamentally different manner to the work published in 2012. They're just faster, better algorithms, better implementations of the same algorithm. So I would still recommend those papers. Do we at some stage plan to update those with public releases of the best and greatest decoders? Yeah, we do, but not yet. So let's see. Yeah, I would say that there's a good starting point for this audience. No, it's not the state of the art, but it's not all public.
And what is a typical threshold for, it says measurement efficiency?
Yeah, measurement efficiency is an interesting question. Usually I associate that with not superconducting technology. It's kind of more a photons term. But let me answer it in the terms of superconducting qubits. So we have measurement fidelity, right? What's the error rate that's tolerable? So if you want to be technical, the measurement threshold is 50% under the assumption that all other gates are perfect. And then it's a smooth trade-off between those two extremes. We are targeting of order 2% measurement error, which some people in the audience will note, hang on, that's above threshold, isn't it? And the answer is, well, no. The nominal of order 1% threshold of the surface code is sort of an average threshold error rate, and in particular, measurement errors can be much higher than that. It can still work. If you have 10 to the minus 3 error, 1 and 2 qubit gates and idling, you can easily have 10% error on your measurement qubit and still suppress errors, no problem. So yeah, it's a trade-off. And we're shooting for 2% ourselves and hopefully 10 to the minus 3 on our 2 qubit gates.
Okay, so this one's actually kind of a general question. I think it's about alternatives to the surface code. It says, is the surface code the only potentially scalable solution?
It's our favorite one, and I'm not aware of one that is better. There are several things that go into that. In geometrically constrained 2D nearest neighbor, I'm not aware of any code that has a higher threshold. So that's really important, since it's the number one thing we can't do yet. We can't build a universal set of physical gates with low enough error rates to satisfy even the surface code threshold, let alone any other code that has, you know, color codes or anything like that, that has an even more stringent threshold. Secondly, you can't just build anything physically. This picture, this 2D array of qubits on the screen is also very hardware compatible. So the fact that it's a square grid makes it easier to design. So, you know, people literally start with a layout of 6 of these qubits with a whole bunch of things that hang off it, and then they can start copy pasting. And that should not be discounted as part of the design process. It's hard to make these chips. It's hard to design them. It can take people months to lay these things out and get it all right. And keeping things regular and repeatable is a not negligible part of the design process. So it is certainly easiest in our hardware to build a uniform 2D square grid of qubits. Regardless of what you then use it for, that is the easiest thing to build. If that is the easiest thing to build, it is really quite likely that the very best thing to put on that is a surface code, standard 4-neighbor surface code. So we are not aware of anything better. Let's put it that way. But we're certainly not closed to other options. We are always monitoring the literature and thinking up ideas ourselves as to, you know, is there something better? The answer is we are not aware of such a thing.
So this is basically, I think you may have already addressed this, but to clarify, there are other codes such as LVPC, convolutional, quantum turbo codes, and so on. What is the reason for selecting surface codes? And is this a simple version of color codes?
So surface code is not a color code. Color codes have the property that you have X and Z stabilizers on top of one another, for example, which this does not have. with regards to the other list of codes, all of those codes require non-local interactions, which we don't have. Furthermore, even if you do have non-local interactions, the thresholds of these codes are either unknown or lower than the surface code. The decoding protocols are either unknown or not very high performance. And that is all for memory. So all of those codes are best designed for memory. Turbo codes in particular, they can be very good for, say, transmission of data maybe, but for computation, you need more than just memory. And these codes don't support computation in a very natural manner. Usually you have to teleport the information you wish to manipulate out of the block code, then manipulate it, and then teleport it back, which leads to higher space-time volume overhead. So if we go back to these kinds of pictures where computation is occurring really everywhere in the computer, you want a code that is optimized for computation, not for memory. So I don't personally think those codes will find a role in a quantum computer. They may find a role in a quantum memory, which is probably more for communication or something like that. As I said, you have to extract information from those codes to manipulate it. And if you're doing that all the time, if you are computing everywhere all the time, that raises the question of why are you even using that code in the first place? Just leave it in the code that's best for computation.
So there are a pair of questions related to multi-qubit logical gates. The first one is, in state distillation, does this require extra connectivity than a 2D grid? And then similarly, how does one perform multi-body logical X operators in a quasi 1D lattice?
Sure. So here you can see a layout of logical qubits and the connector that measures precisely this multi-body logical X. And if you keep these logical qubits in place, you can see that I have enough space in between them to measure any of these other multi-body X operators. If this becomes 2 by n as opposed to 3 by n, so this is a 3 by n design, not much would change. You would need to move all of these logical qubits into a row here, for example, and then when you wanted to measure this multi-body logical operator, you would use the second lane to connect only with the qubits you wish to. So, you sort of would just unfold this. So yes, you can certainly do this in a 2 by n. That's not a problem.
Okay, so one question is maybe related to distillation. How do you make error-corrected rotation gates using surface codes?
Sure. So firstly, you start with state injection. And I know I didn't talk about this very much. So this little red biscuit really represents, first, start with a single physical qubit in the 0 state, Hadamard it, do a 1/8 of a rotation T-gate on the physical qubit. All right, so you just do your best at the physical level. And then what you do is you turn on the stabilizers in a careful pattern and you try your best to expand it to a logical qubit. And if you detect any errors in the process, you discard the state and you try again. So this is the try until success representation of getting a logical qubit that is already in a T state. Once you have such a state, what you can do is use a 2-qubit gate. It's really a ZZ measurement. You can use a 2-qubit gate that applies a T-gate to the precious data. So, you prepare a T-state offline, interact it with your precious data, and that will probabilistically implement either a T or a T dagger gate. So this is the multi-step process. Inject, interact, 50-50 get what you want, classical process to work out what it is that you actually got. And then if it's not what you actually wanted, fix it up with an S dagger gate. So you actually get the gate you wanted.
Okay, so perhaps related to this 3D diagram, are there any advantages of implementing C0 using XX and ZZ measurements over the braiding techniques?
Lower space. So if we come back to that picture, for a start, this is a distance D logical qubit, all in a simple square that is D by D. A braided logical qubit is already much bigger than that. Instead of being D by D, it's 2.5D by 1.25D, just as its minimum size. So you've got a big space saving there. Next, the actual interaction only requires one more D by D patch. I mentioned that these extended prisms are actually only there for the human being so they can see things. They're not really there at all. The real diagram looks more like this. So if you compress this in your mind mentally, you'll see that the total C0 gate requires, even if you're generous, just 6 of these D by D by D cubes. All right. And of course, it technically doesn't even require that, because this one could be doing something else already, as could this be. So it's just very, very much more compact in space and time to do it this way.
Okay, is it possible to use teleportation for transmitting a state over a long distance in the surface code? If so, how can we do it?
Yes. And, you know, I stress that you are effectively doing that here. Let's see. So what is teleportation? You create a bell pair and then you use it to teleport. As drawn, here is the bell pair, and then the measurement is kind of this really long thing. But you could do it the other way. Imagine moving this pole all the way over here. So the first thing we do is we create a really long non-local bell pair. And then when we wish to teleport, we do a smaller version of this U-shape just around here. That's effectively teleportation, to move things different. The main takeaway from this diagram is you just don't need to stress about thinking about that way. All you need to know is that I have data here, I want data B to here. You find any pathway that gets you from there to where you wish to be, and you're good. The code will take care of the rest for you. You don't even need to really think about whether it's teleportation or not.
Oh, sorry, I was muted. How do the overheads associated with the surface code compare to the overheads required for fault-tolerant photonic quantum computing?
Yeah, it's a good question. So there have been some recent papers, some nice papers. I certainly recommend the audience take a look at one from PsiQuantum on a chemistry calculation related to batteries, where they spec it out. So the general feeling is that with photonics, you need more components, but their hope is that these components are cheaper. So it remains to be seen which one of us can get to the necessary level of performance such that the devices work at all. And it should be stressed that neither of us are at that level yet. And then if one or both of us get there, let's assume both of us get there, what turns out to be the cheaper computer, how much hardware you truly need. If you ask me, I think they require a lot more hardware, so much more that it'll be a more expensive computer when it's done. If you ask them, they'll say they've got everything under control. And of course, no one really knows. So my takeaway is that despite their arbitrary interactions, they're not completely arbitrary, but they have more arbitrary interactions than we do, which gives them more options both at the code and algorithm level. Coping with loss leads to so much extra hardware that it will be more expensive. And of course, they'll disagree, and that's very healthy. And I welcome all of that. I look forward to competing with them and seeing who builds the best computer.
Okay, Austin, in your professional opinion, sorry, my screen is scrolling. Let me get back to the question. Oh gosh, sorry. Every time a new question posts. So the question was, what do you think will lead to, in your opinion, what will lead to real quantum computers? Is it improvements in the hardware or improvements in error correction?
No, it's all improvements in hardware now. I feel that there's really little room, if any, to improve the error correction anymore. It's a very mature field. It's only one I've been working for a long time. I don't see any revolutionary in terms of, you know, are we suddenly going to wake up one day and have a 10% error threshold code? No, I really don't think so. So yeah, it's all of the things we talked about at the hardware level that we really need to get right, which are these guys. We need to improve our yield. We need to work out how to make qubits reliably. We're used to making transistors reliably, billions, trillions of them, no problem. But we can't yet make qubits reliably. We need to work out what is messing up the coherence of our system, whether it's contaminants or some aspect of the structure or design, and really get that under control. And yeah, it's not all sort of hardware. When we try to do better readout and reset, for example, this comes down to understanding the physics better, to design better control pulses, to do better reset with the same hardware. So, that's kind of software physics research, but from my point of view at the error correction level, that's still hardware. So yeah, I would love to say that, no, we can save the world with better error correction, but I think that's not likely to happen.
Okay, well, I think we've run to the end of the session. There are a few remaining questions. Some of them focus on hardware technology, especially for superconducting qubits. I believe there's a session tomorrow that will go into detail on that. And there's also some breakout sessions after this. So perhaps I should hand it over to one of the hosts.
Hi, everybody. Thank you so much. So we're actually pretty fluid about our timeline. Austin, if you wanted to keep lecturing, we could probably go for another 15, 20 minutes.
Sure. I'm happy to take more questions. We can keep working through them. That's fine.
Yeah, so we have a rough structure, but it is not in any way rigid. So if it's just, I'll look for confirmation from Eric that that's okay, but let's take
Well,
maybe
that's fine with me. It's just up to Austin and Cody.
Yeah, no, let's keep doing it. If there are more questions,
great.
and I should stress that if you have more questions now, please keep asking them. I'm happy to answer questions till the lights turn out. Not a problem.
Okay.
Yeah, sure thing. I just didn't want us to, slip our schedule, but yeah, I can take a few more questions. So here's a question about error correcting codes. It says, is there anything to be gained by adding energy penalties for error syndrome states? Does this lead to useful error suppression?
Yeah, so people have looked at this in terms of making Hamiltonians that naturally suppress errors. So strictly speaking, the simplest way of doing this, which is you sort of have a 4-body Hamiltonian X and Z term, doesn't work. It doesn't work because there's no energy penalty for the equivalent of detection events to wander around. And I would argue that this is probably not the best way to go. The best computer in my mind effectively has no Hamiltonian. So you can turn off all the interactions and nothing touches anything. There's no crosstalk, there's no noise that's multi-body. You only have any chance of multi-body noise when you choose to interact just one isolated pair of qubits at a time. So that's my belief. Having said that, there are all kinds of interesting qubit proposals out there where they try to use the physics of the qubit better to create noiseless subspaces. And it just remains to be seen whether you can, one, make a lot of qubits with those kinds of physics tricks built into them, and two, whether the theoretical promise of those, so I'm talking about Kursnel qubits and the photonic cat superconducting qubits and 0-pi qubits, fluxonium qubits. There's quite a few proposals out there for qubits that, at least on paper, look very promising. But the challenges there are, can you scale it? One. Two, does the performance really hold up in a larger system? And all I can say is that we do monitor these things closely. We collaborate with people. Sometimes we give funding to people working on these other qubits. So we're certainly interested in these things, but we haven't seen anything compelling yet that says, oh, we should definitely switch to that. When we do, we have in our group a history of switching to them. I mean, this group way back at UCSB days started off with phase qubits, and then we switched to transmon when Yale showed that they were better. And these days we have tunable coupler transmons, and if we ever see something better, we will switch. So at the moment, these are our best guesses: tunable coupler transmon qubits. Other qubits with more exotic properties exist. We'll see if they pan out and take over.
Okay, so I think a question just to solidify terminology. Could you briefly explain the practical and physical differences between measurement qubits, qubits, I believe they meant data qubits, and logical qubits?
Sure. So this diagram really has all of those. In this diagram, one's colored yellow and one's colored pink. And really that's the only difference. Physically, they're identical, literally identical. I mean, it's just a pattern of qubits. It then comes down to how you choose to use them. So we choose to use our data qubits to store information. We choose to use our measurement qubits to interact with them and search for errors in the data qubits. So physically, no difference. The logical qubit is then a group of such physical qubits. So this blue outline encompasses the smallest logical qubit. So here we have 17 physical qubits, 9 data qubits, and 8 measurement qubits that collectively form a logical qubit that guarantees that if any single error occurs, isolated in space and time, it can correct it. And then here's a bigger logical qubit, this green outline. This now encompasses 49 physical qubits, and it guarantees that if any pair of qubits occurs locally in space-time, it will correct it. So the bigger you go, the more errors are guaranteed correctable, and provided the probability of those errors is low enough, the lower the probability that you have a combination of errors that will break your code. So yeah, measurement qubits, data qubits, identical up to usage. Logical qubits, bigger and bigger patches of the same, working together to store a single qubit of data.
Okay, there are a few questions about scaling up. So in contrast to superconducting qubits, can cold atom architectures that use laser cooling avoid this scalability problem because of their scalability in cooling architectures eventually? Or are there other problems with this technology?
Yeah, it's an interesting question. First, in cold atoms, there are a few types. There are neutral atoms, and they do get really cold, and you can have arrays of neutral atoms in laser traps, and that's an interesting technology, indeed arguably one that inspired the design of a lot of these fault-tolerant schemes. The issue there is that they are really, really slow. We're talking gates at the Hertz level now. So I think in my mind that immediately precludes scalability. And as of last check of the literature, there wasn't even a compensation of that slowness with, you know, extreme high fidelity. So they're still struggling to get gates that are even as high fidelity as ours, despite being very, very much slower. So if you don't have the lower rates, you can't scale. And at the moment, that's the case for them. Even if they did have the error rates, the slowness means I think they would struggle to solve anything practical in a realistic time frame. So no, I'm not personally bullish at all on neutral atoms. And I've already spoken about ion traps, which are the non-neutral atoms. They are a lot faster than neutral, but still a lot slower than superconducting. Ultimately, we're building a computer. It's got to run fast.
So you showed some 3D renderings of a 10K and 1 million version quantum computer. So the question is the 10K version different from the 1 million version in that the latter, the 1 million, extends in a quasi 1D way?
Correct. So the 1 million is about 150 of these. Well, technically it's exactly 100 of them. If you want to be really technical, there's of order 8,000 qubits in the design. So we have a quite detailed, fleshed out design of this thing, which is what we are working towards building. And indeed, this is intended to just be many copies of this. So you can certainly imagine as a prototype one day building something like this. Of course, it would have a fridge that encompasses this, but where you are explicitly trying to bring all of your wires out of the fridge in a compact, controlled manner, and explicitly trying to fan out all your wires to your control electronics in a compact and controlled manner, just to prove that you can scale. So yeah, this is many copies of that.
Okay, so you mentioned frequency crowding. So 2 questions. What is the maximum number of qubits that can fit safely within a frequency range to maintain good gates? And it says in parentheses, is it range divided by the Rabi frequency? And two, what kind of challenges does this maximum number of qubits pose for scaling up?
Yeah, we don't really have frequency crowding as such. Let me rephrase that. So there are some types of qubits where you do have frequency crowding issues, particularly when you have fixed coupling, you have frequency crowding issues. Because we have tunable couplers, we can set our qubits, our data qubits, and measurement qubits for that matter, at fairly similar frequencies across the chip. And that does not itself lead to crosstalk or frequency crowding, because then we have the couplers between them, which we can detune and balance out the coupling between them to zero it out. So yeah, we don't really have a frequency crowding issue. The frequency issue I mentioned is that, well, when we do our gates, we need to sweep the frequency of our qubits and couplers. And what you'll get when you build these qubits is some frequencies that they work well at and other frequencies that they don't work well at. And the frequencies that they don't work well at are typically associated with what we call two-level systems, TLSs, which are of unknown origin. So you can just call them rubbish, some stuff we don't understand, and they move. So it makes it very challenging to find a range of frequencies that you can sweep over to implement high fidelity gates everywhere all the time. Having said that, we do have all kinds of tune-up software that does its best to find good frequency ranges for all of our qubits and couplers and does a pretty good job. And then we also have people that go in and tune things up further. So yeah, we don't have a scalability issue from frequency crowding. We have more it is difficult to achieve high gate fidelity everywhere because our qubits don't have good performance at all frequencies. That's more the issue. And the performance at those frequencies changes on a time scale of hours. So you can tune up the chip, can work great for a few hours, and then you need to tune it up again. So we need to work on things like dynamic detection of when parts of the frequency spectrum become bad, and sweeping through those would lead to a bad gate, and moving the idling frequencies of the various components in the neighborhood around to fix that up and preserve good performance, which we don't have yet, but we have proposals of how to do. So that becomes, a software engineering challenge, monitoring the performance dynamically and feeding back to the way you tune up the qubits on the fly.
Okay, could much faster 2-qubit gates, for example, 1 nanosecond, effectively reduce the error rate threshold required for the surface code?
So the threshold is more dependent on the error rate of the gates than their speed, particularly our 2-qubit gates, because in our system, they're already the fastest part. So if we reduced our 2-qubit gates from 20 nanoseconds to 1 nanosecond, and let's assume the fidelity was preserved, it would certainly help a little bit because you reduce the cycle a little bit, but the main dominating timescale is our readout and reset. Furthermore, gates at that timescale, there are no proposals to run gates that fast. Even if there was some pulse sequence that could run a gate that fast, it would require very extreme pulse engineering, and that would be both expensive and difficult to achieve high fidelity. And it's the fidelity we really need. So for my money, if someone came and said, we'll make the gate 40 nanoseconds long, but managed to get higher fidelity, that would be more favorable. So to summarize, yes, we do shorten the length of our gates to try to achieve higher fidelities, because provided you are working at the limits of calibration, shorter means less decoherence means less error. If you go to those extremes, however, you run into more expensive hardware and pulse shaping issues. And I'd be surprised if it was even possible to do a gate that fast that would work at all and be high fidelity. And secondly, even if you could, it wouldn't really help that much. Much better to reduce the time of our readout and reset first.
Okay, a question related to physical 2-qubit gates. IBM systems exploit the cross-resonance interaction, or ZX, and then they use dynamical decoupling to get a reasonably good CNOT gate. is there a relation between the pulse level implementation of gates and quantum error correcting codes?
That's not obvious exactly what the question is asking. Yes, we do all kinds of pulse engineering to lower the error rate of our gates so that we have a chance of implementing error correction. So we use dynamic decoupling during these very, long microsecond scale readout and reset times to help preserve the information on our data qubits while the measured qubits are being reset. We insert Pauli operators in our circuits to try to balance out the noise to make it easier to correct. And you can bet that when it comes to tuning up each and every one of these gates, there's an awful lot of pulse engineering that goes into achieving high fidelity. So maybe I'll just say that yes, every trick you can imagine of to get higher fidelity that we're aware of, we use, and we'll use more if more tricks become available.
I think what they might be getting at is that the cross-resonance gate gives you sort of a native C0, whereas tunable transmons give you kind of a native CZ, and whether
That's
that
right.
makes a difference.
It doesn't make a difference to the circuits. If I go back to like the beginning of the talk, if you have a look at these circuits, they're built out of CZ gates, which is the more natural interaction for our hardware. If you wanted to use C0 gates, you would simply put basically, you can remove this Hadamard gate and this Hadamard gate and just replace these with the C0 gates. So there's a natural way to transform these circuits between a CZ form and a C0 form. So there's definitely no advantage to a C0 or a CZ. They're completely equivalent.
Okay, so sort of on the topic of scaling up, there's questions related to scaling down. Are there challenges, design challenges when shrinking the circuit or gates? And then related, are there efforts to shrink down the size of the refrigeration?
So we don't plan to shrink our qubits. That should be stressed. We don't plan to do that. Already with 1 millimeter center to center scale qubits, the challenge of getting all the wires in is quite extreme. And it seems manageable at that scale, but we don't want to make the qubits smaller. When it comes to compressing circuits, so, this kind of process to get this kind of thing is done by human beings, but software is certainly under development to try to compress circuits more generally. Perhaps I'll just say that at the physical level, we don't want smaller. Fridges are unlikely to get smaller. If anything, we want to make them bigger. This is a really big fridge. We want to make them bigger so we can hold more qubits. And we certainly have research right now going into making bigger fridges. Bigger means they can keep more stuff cold, really. And we need to keep more stuff cold. We need to put more qubits and amplifiers and all sorts of things in our fridges. So we need bigger fridges. So there's no focus on miniaturization of the fridge or the hardware or the qubits. There is a focus on miniaturizing of some of the hardware in the fridge. For example, we have amplifiers that are too big and power hungry. We focus on miniaturizing those. We have filters that are too big and expensive and so on. We focus on miniaturizing those. So there are certainly components in the fridge that we wish to minimize their volume so that we can get to this scalable picture. If your eyes are good, you'll see kind of boxes here and here that contain more compact versions of amplifiers than we currently have. And yeah, there is a miniaturization effort there. If it were possible to miniaturize this control hardware more, that would make life easier. We wouldn't need to have such long cables, we wouldn't need to need such high power. So if we can miniaturize the control hardware, that would be great. If it was possible to minimize it enough that it could fit as little blades on the top of the fridge, that would be great. We don't know how to do that. So the main focus is miniaturizing amplifiers and filters in the fridge, control electronics outside the fridge, and the actual wiring that goes between everything. There's certainly an effort to miniaturize that. The qubits themselves, the fridge, no. If anything, they would be nice if they were bigger. And when it comes to circuits and all of that kind of thing, meaning the actual algorithm level. So this stuff, that's primarily done by hand at the moment.
Okay, there's a question. Could you comment on what kind of challenges might arise from designing a 3D array of qubits with the different qubit systems?
Yeah, people have thought about this. So let's see. Here is a picture, all right? And it looks 2D. It's not actually 2D. The qubits are on one chip and the couplers, these little rectangles, they're on a separate chip. So it's already a 3D sandwich. So one can imagine, well, if you could do that, why not put another sandwich layer of qubits on top and make it 3D? And in principle, you can do that, but in practice, you'll notice that even to service this 2D layer of qubits, we're really pushing the limits of what can even fit around a fridge. And if you doubled the number of qubits per unit area, you would have to double the amount of wiring and control electronics. And so it doesn't look very feasible for wiring and control electronics reasons to go to 3D. And that will remain true for as long as the control electronics takes up as much space as it does. A qubit needs a lot of care, right? It needs microwave pulse generators and shapers and schedulers and all sorts of things that just physically take up a lot of space on a PCB. And, you know, I've seen people in the literature say, oh, you know, we're going to fit all of the control hardware into a square micron. We look at that and go, well, good luck with that, because we have no idea how all of our substantial electronics to care for each of our qubits could possibly be so small. Right now, you know, we have big racks of custom electronics and microwave pulse generators and all sorts of things that take up liters, and it's really not clear that that can be made tiny. We are hopeful that it can be made small enough, but not tiny.
Okay, there's a question. What are the limitations to reduce the time for readout and reset?
That's a good question. So one of the limitations is when you read out, and I stress a lot of these questions are running into territory that John Martinez tomorrow will be able to give you much more detailed and glorious answers to than I can. You know, my focus is error correction, but I'll do my best. One of the issues when you read out is you apply a microwave tone to a line and it gets a whole bunch of photons in it. And those photons need to be removed at the end. So there's a certain ring down time for readout. Another is if you think about how readout is done, so you apply a microwave tone, and then the state of the qubit will either slightly phase shift that tone or not. And you can't instantaneously detect a phase shift. It takes a certain amount of integration time to be sensitive to whether the shift has occurred or not. So part of that sensitivity is how good your amplifier chain is. And so we have, you know, over 100 dB of gain, so like 10 orders of magnitude gain from our chip to our actual readout hardware, and we'd like even more, but it's very hard to maintain a good signal to noise ratio when you are amplifying that much. So a lot of it is limited by our amplifier technology. When it comes to ring down, you want to be able to dump the photons out quick. That sometimes means you want dissipative elements or less high quality elements on your chip, and then you have to be careful that it doesn't impact the coherence of your qubits when you have such elements around. So it's a balancing act, having damping and enough amplification to have short readout and reset.
Okay, is it correct to assume that we need to first do a good pulse engineering to get high fidelity gate, and then do quantum error correction to get an error corrected logical gate?
I'll say yes. First, we need very good individual gates before we can possibly do error correction. So our best gate that we've ever done, 2-qubit gate, is around the 99.8%, but more typical is about 0.5% error. And really in our dreams, we'd like 5 times less. We'd like our average error to be around the 10⁻³ level for our 2-qubit gate. And we're just not there yet. Right, we need to control all of these things on the screen at the moment to get closer to that goal.
So there's a question to clarify this diagram, actually. It says, for the larger ring in green, how come the data qubits on the corners don't have the additional measure qubit that sits right behind it that is not used?
So for example here, yeah. So it comes down to, does it need to be there? And would it be consistent with the actual stabilizers of the code? So let's go back to the very beginning and look at the stabilizers of the code. So basically you're talking about this one here. So the thing that goes here would measure an X stabilizer. But if you put it in here, an X stabilizer here would anti-commute with this Z stabilizer here. So, you know, it wouldn't form part of a sensible logical qubit for that to be there. Your logical qubit must be defined by a bunch of stabilizers that mutually commute. And when you cut out a 2D array, you need to cut it out using this shape and explicitly remove this stabilizer so that you have a well-defined boundary of commuting stabilizers. So yeah, it's of necessity to ensure you have an array of commuting stabilizers.
Okay, so I think referring to the quasi 1D architecture, it says, we do not know exactly how many logical qubits we can have, since it depends on how many spatial units are required for state distillation and qubit movement during the computation.
Correct, yeah. So it's more accurate to focus on, so, okay, let me just plot a picture, right? So what is the question getting at? When you look at this, how many logical qubits are present? Well, in some ways, this shows 1, 2 logical qubits. All the rest is just stuff that generates these outputs. And so, yeah, it's good to focus on what is the algorithm that gets implemented rather than the number of logical qubits. Here, some of the logical qubits are really small. These are logical qubits. So are these, and so are these. So, you know, counting logical qubits is not the most productive thing. It's much better to say, we would like to work out some particular chemical property of some particular reaction. How many physical qubits are required to do that? And that's ultimately all that matters. Counting the number of logical qubits is kind of pointless. Here, I would say there are 2. We produce 2 T states with all of this. So yeah, it's a good comment, and definitely good to focus on what those qubits collectively can do rather than how many patches are really logical qubits.
Okay, so one final question. It says that NIST demonstrated using RF control over fiber to control a superconducting qubit. Will that be the future of what control looks like?
Maybe. So we do have an internal project that looks at cold control. So essentially, can you take everything that is, well, maybe this one's the best one. Can you take things that are out here and move that control into the fridge? So the short answer is maybe, but you would only do that if it gave you an advantage in fidelity, because we have no fidelity to play with. See, it would be different if by doing all of this crazy business, we got, 10 to the minus 4 error, and then we have some fidelity to trade off for simplicity. We don't at the moment. And certainly the concern is that if you move away from these kinds of clean control systems to cold control inside the fridge, it simply may not work as well as these off-the-shelf, very high-quality systems. So the best we can say is maybe. Only if things improve a very great deal in performance. It's desirable, because then you could imagine having cold control somewhere in here and reducing a bunch of wiring, which introduces a whole ton of extra heat load, and that's extra electricity to keep the whole thing cold, right? Keep in mind, all of this wiring conducts heat. And when you have a fridge that has heat conductors through it, that means the fridge needs to be really powerful. So there's a real dollar cost to having this wiring there at all. If it were possible to put all of the control electronics down here at the liquid nitrogen level and get similar performance to what we get when all the control electronics are out here, yeah, we'd do so. But this is very challenging. Many of the things that are cold are not that small. So You know, out here, we can use the 10 nanometer, 4 nanometer tier 1 electronics, CMOS. So everything can be very compact. In here, you probably can't. And then you have to ask yourself, well, what did I need to throw away to go from here to a less dense technology and still get high fidelity control? So it's going to require some pretty clever engineering to achieve that. So the best we can say is maybe.
Thanks so much, Austin. That was really wonderful. And Cody, thanks for fielding all the questions. That was a really productive conversation.